So till now we have talked about lists which are good but not as good as what we want called arrays, and the reason is because in scientific computing we tend to work with numbers a lot, and we'll want to work with numbers which are of homogeneous types, as in like I don't want to mix integers and floats and complex numbers and so on. So first let us try to do something that will result in something unexpected. So let's say you have a list called list called x with two variables 2 and 3, two items 2 and 3, and you do it 2 times x. So what happens is this multiplication operator in lists is defined in such a way that it multiplies the list by 2. It's like a list plus list. So it creates list and appends it twice. That is something that you won't need in most cases. In some cases you may need that, so depending on what you want, but this is how multiplication or star operator works in lists. Addition, again, if we add two lists, let's say y is 5 6 and you want to add x plus y, it simply concatenates y at the end of x. Okay, so this is something unexpected, something that we do not want in lists. So this results in a motivation to have arrays. Okay, so that is when we move to arrays, and we have briefly talked about it, but let's play around with them for now. Now we'll go to IPython again. So let's say I have a list x which has two items, one is a float, one is an integer, and I want to convert this to an array. So I will have to use the array function. So if I write array, nothing happens because array is available in NumPy module, and NumPy is not imported yet. So I'll say import NumPy as np. So array will be available through np.array. So if I do np.array, now I can see that it's a function NumPy array available, and then I simply have to say np.array of x, and I can put it into x underscore arr. So this x underscore arr is an array that we have, and x is just a list. So you see one difference, that it explicitly tells you that x underscore arr is a type array, and it also converts everything to a real number. So I started with 1.0 and 2. Now I get 1 point. 1 point is simply as 1.0 and 2 points. So both are real numbers. So it tries to convert everything to the most general type that you have in your list. And we have also seen the square root function in NumPy. So it's a type ufunc. So ufunc are functions which can be applied to arrays. So I can apply this to x underscore arr, and that gives me the square root of the two numbers 1 and 2, and returns that. That does a component wise operation on the square root on the array that we have. Okay. So now with this, let's say we had a y list which was list comprising 3 and 4. So if I do an x plus y, you see that it concatenates, but if I convert both of them to array, which is by saying simply np.array, that's a quick way to do it. So now it adds the two arrays, and that is what you want in most cases if you're working in scientific computing. All right. So from now onwards, we'll tend to use arrays if we want to do any kind of a mathematical operation to them at any stage. So as I said, unlike lists, all elements of np.array will be homogeneous, so they'll have the same type. So if it will convert to the most general type that it can. You can also explicitly specify the type. So if I say np.array and then I specify a list, and then I can specify the data type. For example, in this case we are saying complex. So it converts everything to complex numbers. So when if you print the value of x, by the way, this print is from Python 2, but in Python 3 print is a function now. So if you print bracket parenthesis x, it prints the value, but it converts everything to complex number. So it's 1 plus 0j, 2 plus 0j, and 3 plus 0j. So now I can multiply things by complex numbers and it will return something. So you can change the type also explicitly if you want. And typically we tend to use them for doing matrix operations. So here what we have done is we have defined a 3 by 2 matrix. So technically what we see is that a matrix is a collection of rows or collection of columns. So here we define them as collection of rows. So if you have a matrix like this which has 3 rows and 2 columns, so you would specify that as an array which is initialized from a list of a list. So you start with 1, 2, 3, 4, 5, 6 and that is a list which has 3 lists in it, 1, 2, 3, 4 and 5, 6, and then you convert that to an array. So it becomes this kind of a list. And again I had only one real number here, one float, everything else was an integer, but it converted everything to a float because that was more general in this case. So A in this case becomes an object of type np.array, and that array object has a data attribute called shape. So if you call that, it gives you the shape. So it has 3 rows and 2 columns. There is also a dot t, a transpose operator. So what that does is it returns it has information about the array which is a transpose of the initial array. Okay. Now if I define an array which only has one dimension, like in this case 1 comma 1, you do a transpose, you don't see anything, because in this case it only had one dimension. Okay. So there is nothing like a row vector or a column vector in case of NumPy arrays, because it only had one dimension. So you write it this way or that way, it stays as one dimensional object. So transposing a one dimensional array has no effect on its, or we call it rank of an array, but I'll use that terminology later. But you get the idea, right? So it was only one list. There was not a list of a list, so it doesn't matter. But if you are using MATLAB, for example, then in MATLAB you would define a vector as either a row vector or a column vector. So you will call it size 2 comma 1 or 1 comma 2. But here we don't do that with rank one or one dimensional arrays. So when you use them, you will get used to it. Typically what do we do with them? We tend to multiply, we do some mathematical operations. So here we have a matrix A and a vector x. So I will define this matrix A as 1 comma 2, 3 comma 4 and 5 comma 6, a list of list, and then call the array function. So that converts that to an array, and then I call well x, which is rank 1 array, and then to multiply them I would use a dot function, dot function. So I will say np dot dot, so dot function is available in NumPy, and then I use pass two values, the first one and the second one. So it does an a dot x, that is a matrix vector product, and this is what you get. If on the other hand I had done a star x, it would have done something different. Okay, so it would have multiplied the first column of A with the first element of x and returned that as one column, and then it would have multiplied the second column of A with the second column of x, second element of x, and given that. So it would have been a matrix of size 3 by 2. It won't add, it won't take a linear combination. Okay, so be careful that if you want to do a dot product, you have to use a dot function, not a star. We can also do a dot product of A dot transpose and A. So that's a matrix product. Now there is also a matrix function available in NumPy. So if you really want to work with something that looks like MATLAB, you will use the matrix function. So in that case, in matrix function, you would say np dot matrix the same way, and then if you print the value of A, this is what you get. In fact, it also has a way, it's an overloaded function, so you can specify the contents of the matrix using the same MATLAB style as a string. So it will parse it and it will figure out that this is what you wanted. So the first row semicolon, second row semicolon, third row, and then quotes. The good thing about using matrices is that then star operator, multiplication operator works. You don't have to use the dot function. You can simply say A star X like we are doing here. But then again you have to work with matrices. So if I say X, I have to define whether it's a column vector or a row vector. So here what I have done is I have called it a column vector. So now if you print the value of X, it is actually a list of lists. So it's a two-dimensional object, except that it only has one column. So now if I do an X dot T, then it returns a matrix object which is different from X that we had earlier. But in arrays, that was exactly the same, the object. Okay, so if I do a star X, it actually does the dot product between A and X. Now when you index matrix objects, then they are slightly different. So in arrays what we did was we said X 0 bracket 0 bracket, and then we had bracket 0 bracket, but here you would say X bracket 0 comma 0. So again very similar to, I think MATLAB also does similar way of indexing. Okay, so these are, I mean, you can try these things yourself. There is no point doing a demo here. I would rather spend the time for demo on the timing commands. So whenever we need these things, we can try it out. But linear algebra is something that you would most probably be using if you haven't used yet in Python. So the question is, I mean, in which case would you use an array, which case you'd use a Python matrix? Typically arrays are faster, so we'll tend to use arrays as much as possible. But if you are really converting a MATLAB code, you're comfortable with MATLAB, you tend to work with matrices a lot, then you'll use matrices. Otherwise, in most cases, arrays are standard. Okay, when I say, so ones actually is a function similar to what we have in matrix. If you want to initialize an array of a certain dimension, then you will use np.ones. So that what it does is it creates an array of size 4, 4, so 4 rows, 4 columns, and everything is equal to 1. And then you can start, then you can modify the contents. That's one way to define, create some memory location having a certain type, create an object of certain type. And if you use a rank function here, np.rank, that gives 2. So this is equal to the number of dimensions you have in this case. It's a two-dimensional array. Okay. You can also have higher dimensional arrays. So here I have done np.ones 2, 2, 2. So this 2, 2, 2 actually is a tuple. Remember, tuple we said was it's in parentheses. So this is a tuple. So that's a way to, that is what you pass to ones function. But this case you have 2, 2, 2. Okay, so this is a rank 3 array. So if you had to plot it, it would be a matrix, and then there's also be a third dimension in the matrix. But if you print it, it looks like this. It's a list in a list in a list. So if I say t of 0, that will be the first object. So that will be 1, 1, 1, 1, this list. If I say t of 0, 0, so that will be the first item in the first item of that t list. So that will be 1, 1. Then if I say t 0, 0, 0, that will be this item. Okay. So if I say t 1, 0, 0, that will be this item. Again, it's best if you practice it yourself. It's very boring if I do it right now in front of the screen. But the whole idea is that you can, in arrays, you can have as many dimensions as you want. So if you work in physics where you tend to work with n dimensions, then it's very useful. Next thing that we tend to use a lot is called the solving Ax equal to b, okay, linear equations. So here in MATLAB what you do is you use a and the slash operator. Okay, so those who have used MATLAB, they know that. Here what we do is we use something called solve function is available in NumPy. In fact, NumPy.linealgebra, linalg. So what you do is you say from NumPy.linalg import the solve function, and then you solve a comma b, where a is the matrix and b is the right hand side, and then it returns you the value of x by solving it. So if you have to solve a system of linear equations, you will specify the matrix A and B as A being an array of type of some dimension and B being a vector or an array of rank 1, and then you give these as arguments to the solve function. We also tend to use calculate eigenvalues in linear algebra. So there we use the eig function. So whenever you solve the eigenvalue problem, you get eigenvalues and eigenvectors. So you're solving Ax equal to lambda x. So for every for any matrix A, you will have eigenvectors and eigenvalues. If it's symmetric, then you'll real symmetric, then you'll have n eigenvalues and n eigenvectors. So in that case, when you solve the eigenvalue problem, you get eigenvalues and vectors, and they actually are returned as a tuple. So when you say eig of A, it returns an array where the first it returns a tuple where the first item is an array which contains the two eigenvalues, and the second one is an array which contains your two eigenvectors. So it's basically a 2 by 2 matrix here. So then you can unpack this tuple. So you can say that whatever if you say result equal to eig of A, you can say result of 0 and result of 1. Result of 0 will refer to the eigenvalues, result of 1 will refer to the eigenvectors. Or you can also unpack the tuple this way. If you specify evals comma evx equal to eig of A, then automatically the first item of the tuple goes to evals and second item goes to evx. That's a very standard way to unpack tuples which are returned from functions. So I've included two references here which are for you to explore further. So that's sort of the end of discussion on Python, more or less, apart from a couple of things that most probably we'll discuss next time. So do explore these books. One of them is more general book on Python. The other one is particularly about scientific computing. So F strings I have already talked about. So these are Pythonic way of doing things. We already have talked about F strings. So they were introduced since Python 3.6. But let's explore it a bit further. So if we have a number t equal to 1.234567, so if I use an F string and say a t in these curly, then it converts that to the actual number. So it prints default value, output gives t equal to the whole value. So it will try to figure out whatever default is the best. But if you want to control the formatting, you can say t colon dot 2. So that means that you want a precision of 2 digits. So in a number of this kind, if you want 2 digits of precision, it will be 1.2. If you want a fixed point notation in the sense that you want 2 digits after decimal, then you say t colon 0.2f. So then you are saying that you want 2 digits in the fixed point notation. If you say 10.15, that means what we had discussed earlier, that it is a total of 15 digits that you want in the whole number. And then well, it's very useful. We don't use the percent symbol that was used earlier for printing things. Now there is another thing called a zip function, which you will see a lot if you read Python codes. So if you have two lists of the same size and you want to iterate in the elements, okay, so let's say they are coordinates. So you have x coordinate list and a y coordinate list, and you want to iterate through all the coordinates. So you can zip them into a common list, and then you can say for low comma high in this. So then it will iterate through the two lists, and every time it iterates, it will pick the corresponding elements of x and y coordinates. So that will allow you to refer to all the coordinates at one go, rather than having an item I and then you say a low of I and a high of I. So that saves some coding effort. List slicing we have sort of discussed how to go from one element to the range of elements. There's also a membership thing that you can read yourself. We're out of time now, so I want to finish on time today. So let's stop here, and then next lecture we'll keep on Python. I'll talk about quadratures, lambda functions, the idea of main program, and then finally an exercise that we'll do together in the class that uses the timing module of Python. Thank you.